So welcome to the 2024 WRRC KY seminar series. So today we have Dr. Albert Kim, professor and graduate chair in the Department of Civil and Environmental Engineering at the here. Okay, so his research actually ranges from the still with the very various areas. So, but in this direction, he is working on the membrane and thermodynamics, renewable desalination, energy production, and also dissipative hydrodynamics for the small scale confined granules and suspended colloid and cellular aggregations and associated modelings. And also broadly, he's working on the parallel computing of the fluid dynamics for membrane separation and wastewater treatment. Okay, Dr. Pim previously awarded the National NSF Career Award in 2005, and also he got the UH Regents Medal for Excellence in Research and Medal for Excellence in Teaching and other numerous awards. So I just give the vote to you, and so thank you so much for accepting our invitation. It's all for you.
All right. Thank you so much. The warm introduction for me. Desalination is always my pleasure and passion, something that makes me excited. Yeah. So, well, I'm teaching currently 330 in CEE, the environmental engineering. There's only one section for membrane in 1 hour. So I even didn't cover the the membrane just for an hour, but it could be a 1 or 2 semester entire course. So the desalination is the big theme. However, today what I really want to mention and emphasize is that it is way more than what we expect. So engineers' contribution would be way less than what we are thinking, and there's a lot of room that we actually have to go and contribute. So let's see. So desalination, the definition of desalination means D means removing and salt, salinity, obviously salt. So salt is technically the some ingredient that makes our food salty, sodium, chlorine, and even magnesium and other kind of positive the ions, and those are most likely what we call the salt. And we actually have to remove the salt from the seawater by certain purpose because we don't have enough water. And so couple of questions, very common sense question is, why do we need desalination to produce a fresh water? If so, then how much? And if we have to do desalination, what would be the best technology? And is it kind of affordable by the state of Hawaii? And those are kind of questions that I have for a long time. And actually, this is a universal question to anywhere else. Okay, so let me start kind of big and then get into the small steps. So we are now living in 21st century, located in the state of Hawaii. We're in the middle of Pacific Ocean. So if you zoom in the Hawaii map, then there's no land outside of this Hawaii island. Even if so, we kind of having kind of confined life geometrically. That we kind of need to know that how worlds are moving and then what are the current status of the world and how we gonna prepare our life better starting right now. So there's a couple of terms that define the 21st century. Yeah, 21st century is the century of climate change, century of sea level rise, century of population explosion, pandemic disaster, which is new that I just added, and new global governance, meaning that US was leading the world, but right now this paradigm kind of changing, and then depending on which country makes more money and what are the pros and cons of each country. So it is more likely, rather than governing, is a sharing paradigm is a future kind of politics as well as economy. So economy is often defined the 21st century as a sharing economy. For example, you have a one ocean between two nations, and if one nation catches all the fishes and even small ones, the next year then there's no fishes. So there should be a certain sharing paradigm between two to optimize the performance and also to minimize any disaster or disadvantages. And the last one is quite important for us. It is a century of resource depletion. Okay, so we wouldn't have any enough resources probably 100 years later or 80 years later. So we kind of do not know what's going to happen by year of 2100, 80 years later from now. So that is the time that I'm not gonna be here. So I kind of want to pay more attention on next few decades. However, we need to know, or we need to know some what others are talking about 80 years later, and to prepare the tomorrow better. So these seven kind of characterization of 21st century is something that the academic tasks. So for example, who can address these problems? Most likely scientists, natural scientists, well, who are good at math, physics, chemistry, and biology, applied scientists, engineers, obviously, civil and environmental, chemical, mechanical, electrical. I believe that industrial engineering become more and more important in next few decades because it is the only one who could directly link orthodox engineering or applied science to the infrastructure and the social aspect. And social scientists, sociology, psychology, and economics are less regarded in engineering. However, these are quite important, and that could be almost like a determining factor in next few decades, the projects and other works by engineers. So what is the definition of science? And here are a bunch of definitions in science, but most likely science implies observation, experimentation, and make a lure. And this lure is sometimes lemmas and sometimes it became principles and laws and theories, right? So every single science are based on observation, and we could just observe passive way, or we could do some better observation based on what we know and what is set up. So here, sampling method is number one, we observe, just observe and looking at by certain phenomena, make a question and make a hypothesis, experimental thingy, and analysis and conclusion. And if these are not matching each other, then you actually have to do again and again until you get a self-consistent logics. So the good thing or one thing that we not kind of always emphasize or remember is that the science that we are talking about is fully based on reproducibility or repeatability. So if you do certain experiment and write a paper to Nature, but next day you don't get it by changing something a little bit. So if you couldn't reproduce, or if your industry couldn't reproduce anything that they couldn't make kind of products, okay, in a stable manner. So reproducibility is sort of the minimum requirement for any science. However, what we are having in the next decades are not reproducible. So climate change, can you set up any experiment to study the climate change? Well, you just cannot. Cerebral rise is somehow the phenomena that it will occur, but we don't have any control. We just observe it and try to minimize impact of cerebral rise to human life. Population explosion, no way. And then pandemic disaster, you see what other, all the world nations are doing right now. And we just don't have anything we could just control pandemic disaster. New global governance is all about the politics and shared economy. So this one should be sharing economy is out of our kind of territorial concept. But the common factor that you actually have to know from item 1 to 6 is it is not reproducible and no one can set up anything. It is a single unique event along the timeline of human history. Okay, but only thing that we can touch and handle and address is number 7, resource depletion. So what do you mean by resource? Those are most likely even NSF address like that: food, energy, and water. Okay, And to generate the food, and I mean, human need food, but to generate food, you need energy. And to produce energy, you actually have to have water. Yeah, you cannot make any energy almost if you don't have enough water, and even for the cooling. Okay, so to me, the water is the most important kind of resource, natural resource on the earth. Where in Hawaii we have excellent air quality, and we have enough and very clean water. So sometimes we don't appreciate too much, but we actually have to remember every day that we are living in a very very blessed land. So population, you look at the population. So to make it short, that world population right now is 7.8 billion. Okay, and then it will increase by 2,100, 40%. So 3.1 billion will be added on top of 7.8 billion. Therefore, obviously the population will be more than 10 billion. And where these people come from? Mostly from India, unfortunately. Well, I'm not saying anything about this country, but technically China, the population decreases, a little bit decreases, yeah. And U.S. population is always kind of stable, and other countries kind of fluctuating. But the biggest contribution to the world population explosion is from India. And you may know that these countries, none of them are in the cold region. They are all in the hot region. Therefore, the cooling energy is also important factor. So global freshwater demand from China, India, and US, actually India, this demand increases actually double from the 15 years, from the 2015 to 30. And then what we need to have more by year of 2030 is actually kind of double of what China and India is using. So total amount of water demand that China and India need right now, or probably yeah, right now, that is actually what we have to prepare on top of what the water resources available at the current moment. So that is actually a serious problem that we don't perceive too much, but it is what's going on. So how much water do we have on the earth? This is my favorite slide from USGS, that all water, this one, so if you collect all the water on the ocean and make a one water drop, and the size would be this much. It's not that hot, not that big, because the waters are kind of existing on the shallow surface of the earth. If you compare the ocean depth and the radius of earth, then ocean depth is kind of negligible. The freshwater, the small one. So you actually have a very small kind of sphere in here. That is actually the radius is, yeah, diameter is about 34 or 35 miles. So that is actually obvious in here. This is the ocean, and that is actually fresh water, but not that available. Yeah. But so this water is actually a non-saline water, but not fresh enough for us to treat right away. So the amount of water that we can share by the world population is this much. Okay. And so we know that the population will increase about 30% in next 80 years, but amount of water would be similar. In that case, we actually have to save 30% of water that we are enjoying right now. So in terms of natural resources, then the next decade and the next until probably 2100, that's many decades, that the human will have a tougher life in terms of lack of enough natural resources, especially water, and that will somehow influence the world economy as well. So USGS, this is public information, and but I should say it's not very accurate, but older is okay. So total water supply in the state of Hawaii, that is about approximately 270 million gallons per day. That is 900 K tons per day. So it's approximately about 300 or 400 Olympic size pool size. And then other data are kind of general data that we have. So average water use per capita is 210 gallons per day. That is about 800. So right now the average water consumption per day per capita in US is 670 something, which is way more than what Europeans use. European people use almost like 30% of water that we are using. And so water consumption is also another problem that we actually have to readdress. On top of it, the cooling is another important factor that we don't usually keep in mind. The thing is that, so here we have a certain way to define how much cooling that we need. Cooling degree day means today's temperature in Fahrenheit subset by 65 degree Fahrenheit. So when I just first time saw this one, wow, 65 is too low. And recently I figured out why they use a 65 degree Fahrenheit. That is actually 18.3 degrees Celsius, which is just half of a human body temperature. So you actually, this temperature difference multiplied by the 365 days to make it annual value, and then you multiply the population. So that is actually cooling energy demand per nation. The highest one is India. It's way higher, followed by China, Indonesia, and Nigeria, Pakistan, and Bangladesh. So if you look at this one, and actually there's only 2 to 3 developed countries. Those include United States, Japan, and Saudi Arabia. And all other high cooling energy demand nations are kind of being developed or developing countries, which they need more kind of better infrastructure to use energy in a efficient way. So these are the types of desalination technology that we could use, and I can explain better later. So Brown just found the Brownian motion in 1828. Then Fick developed the Fick's law 1855, and that time it was sort of empirical correlation, but now we just accept it as a law. And osmosis was found by the Jacobus Hendrikus van 't Hoff in 1901, and he got the first Nobel Prize in chemistry. So what the osmosis is that if you have this water and concentrate solution, and if you remove this water, then actually there should be some spontaneous mixing. But however, since this wall or membrane is semi-permeable, only water can move. So instead of solid moving in free space, due to the presence of this membrane, water moves. That is to minimize energy difference between two phases. So water moves until it it reaches certain equilibrium due to the pressure difference due to gravity and the osmotic pressure. And reverse osmosis was found or developed in 1960s at UCLA and by two people, Loeb and Suranjan. And then Loeb recently, not recently, but 10 years ago, he passed away. And currently, the world's largest and cheapest reverse osmosis design plant is Sorak in Tel Aviv. And it can handle like 624 kind of thousand tons per day. And amazingly, the production rate is actually below 50 cents. So $0.5 per ton. One ton means that 1 meter by 1 meter by 1 meter. And then they sell the water to Israel, the water authority. But if you compare this water price, way low than our daily life price. Technically, Evian, the bottled water has this about kind of cheapest rate, about more or less $1 for 330 milliliter. If you converted this into ton, that is actually 2,000, almost $300 per ton. And while this Israel produced like 50 cents per ton. So the water price that we are just spending today to just purchase one bottled water is about 5,000 times higher than the desalination water produced by this plant, Sorak and Israel. And the other one is the pressure retarded osmosis. So in principle, this pressure retarded osmosis could be applied for anywhere in the world where the estuary could be found. Yeah, the Sorak plant is a seawater desalination, seawater SW outer plant. Yeah. And then it was previously Sorak. Before Sorak, there's one called Ashkelon. Ashkelon was the world largest for a while, but Sorak took it over. But Ashkelon's the capacity is about the 30 or 50% of Sorak. So those two seawater desalination plants are world largest and actually exist in the Israel. Okay. Power. Oh, that's well, I can discuss this later. All right. So we have well here we have three different types of osmosis: FO, PRO, and RO. So FO is like that. So suppose you have feed commonly for the seawater, then we could prepare what you call a draw solution that is a 3 to 5 times more concentrated than the seawater. So in that case, water moves from seawater side to the draw solution side. And the dilemma is if we could easily remove this solutes that we are making draw solution, then actually this could be the one of the protocol for new desalination. But actually, so far the people couldn't find and other application. So this is actually for started from for the desalination, but PRO is to get the mechanical advantage. Since water spontaneously move from lower concentration side to higher concentration side, so in that case, you could use feed as a river water and draw solution as seawater. So due to this spontaneous moving of water and this side, seawater side, the pressure increases as much as water is transporting through the membrane. So in that case, we could use this increased pressure to operate something else. Yeah, conversion is a little bit kind of low, efficiency is low. However, if you have a very efficient energy recovery system, and the mechanical power or pressure induced by concentration gradient is actually the free source to make energy. And the reverse osmosis is we have seawater in here, and then feed water. Feed water is actually seawater, and then this is the fresh water. Then we have osmotic pressure. So water try to move the fresh side to the salt side. So we actually have to apply pressure way higher than the osmotic pressure to squeeze out the water from the seawater. Okay, good. The next one. And this is how the forward osmosis is working. So you actually have a seawater feed, and then you have a draw solution. So water is actually moving from seawater side to the draw solution side. Okay, but the draw solution, the solute that we are making draw solute is very special. So either it is well recovered or it is kind of volatile. So we try to find out the good solute candidate to remove very easily. So in that case, we are using osmosis to take out the water from seawater by preparing special draw solution. And then we have less energy demanding processes to remove draw solute. That is actually the basic idea of forward osmosis. The forward osmosis has been researched almost 20 years, but engineers, we so far could not find magic draw solute. Okay, so technically right now, the forward osmosis is utilized for water dewatering process or food engineering, or anything that you actually have to take out the water, make the solution more concentrate. So forward osmosis can be used for the sludge dewatering, or you could make the certain precious liquid more concentrated. Those include wine and the milk and juice. at the low quality because the salt passage is still existing. So you couldn't 100% prevent the salt passage from drosolute side to the feed. However, this one is could be very well utilized for the fertilizer and application. OTAG is one thing is quite similar to membrane distillation. So this experiment was done in 1926 at the French Academy of Science by the person called Georges Claudius. What he did is actually he prepared 20 liters of kind of warm temperature water and then put this one in the ice. Okay, and then there's some nozzle and there's turbine. This is turbine is nothing but the windmill, very very small windmill, and then the generator is attached. Initially, he pumped out all the air inside and then closed the top. So at T equals zero, this phase is actually the almost like low quality vacuum, and then water starts to evaporate, and then it makes a certain kind of fast wind, and it rotate the small windmill, and then the generator just light up the lamp, and it comes down to the ice surface and it condense. So technically, when the phase was vacuum, that causes the water evaporation, but in steady state, then water evaporates as much as the previous water condensed in ice phase. So surprisingly, this lamp was turned on for 8 minutes. And that is actually kind of a groundbreaking work that you actually have a temperature difference, then you could generate electricity. That's why the OTEC in Hawaii is very famous. And like 500 meters or 1 kilometers down there in the ocean, the temperature is 5 to 8 degrees Celsius. And near the tropical region, the surface water temperature is about like close to 30. So whenever we have a more than 20 degrees Celsius of a temperature difference, that we could generate electricity. But the initial investment was enormous. That's why the OTEC is not that much popular. So this is actually the diagram of OTEC that we could build in onshore and offshore. My idea was that if the OTEC uses water evaporation, why not we use the membrane distillation, which is kind of more compact, and we could make evaporator way more efficient if we use vacuum membrane distillation kind of protocol. Okay, we should be very proud of this company, the Makai Ocean Engineering. They have only like 30, 40 people down there and the east side of Oahu. But this company is world famous due to by having a very special technique, uh, the managing the deep high pressure pipe to be installed in the bottom surface of the ocean. Okay, here are certain things that we actually have to keep in mind. Well, there is some cost that we actually have to pay, otherwise, and we just cannot do it. So here you have a heat added, and this is temperature. At 0 degrees Celsius temperature, the water can exist as ice or liquid water. So if it's already frozen, then it is in the ice phase. And to melt 0 degrees Celsius of ice to 0 degrees Celsius water, then we need to put 333 kilojoule per kilogram of water. Okay, that is kind of reasonably okay, the heat amount. And to increase the temperature of liquid water from 0 degrees Celsius to 100 degrees Celsius, still this is water, we need 417 kilojoule per kilogram. Surprisingly, to evaporate 100 degrees Celsius water to 100 degrees Celsius of vapor, we need this much, 2,256, which is like almost like 7 times of a melting energy. Okay, so another kind of research that I'm thinking right now is that if we freeze the seawater, then some of salts are rejected because water molecule would like to coagulate each other, and they locally repair the salt. So seawater salt is actually kind of a better applied for in real world and the fishery industry. So incorporating this freezing desalination is one thing that I'm thinking right now. And then I believe it has certain potential in Hawaii. But we cannot always increase temperature up to 100 degrees Celsius. That's crazy. And it's a waste of heat. And even if we could, then actually the 100 degrees Celsius, this water will generate a lot of waste heat that we don't use. We just release to the environment, which is not that good. So technically, water evaporates depending on temperature as well as pressure. So if you reduce the gas phase or air phase pressure down to the 3% of 1 atm, water evaporates at 25 degrees Celsius temperature. Okay, that is what we use for membrane distillation. So in membrane distillation, we have a hydrophobic porous membrane, and pore size is approximately zero point 0.1 micrometer, about 100 nanometers. So you introduce the two different types of water. One hot water. This water is 40 to 70 or 80 degrees Celsius, not even close to the 100 degrees Celsius. And then you have cold water. What happens is that the water evaporates on the surface of membrane, and then this evaporated water, which is vapor molecules, migrate through the membrane and condense on the cold water side. So in this case, we don't do anything. Yeah, we just prepare the membrane and let two different temperature flow just go through in the counter current mode. So in that case, we can easily get the fresh water because water naturally or spontaneously evaporates from hot water side to the cold water side. The point here is that how much heat energy that we need to keep the warm solution, feed the solution at high temperature. So the higher the temperature, we could get the more fresh water by evaporation. So in that case, we actually have to find out the local solution to get the inexpensive energy source. Okay, so membrane distillation has four different types. One is a DCMD, direct contact membrane, sweep gas, and vacuum and air gap. And your left-hand side is all same. Hot water is introduced. And other side, you have a cold water flow. That's what we call direct contact. Or we can just use air, less humid air, to take out the evaporated water out of the vapor molecules. That is what we call the sweep gas. And you can just let have the vacuum. So this is not the perfect vacuum, but low quality vacuum. So the pressure in terms of ATM is below like zero point 0.1, yeah, below zero point 0.1 ATM. Yeah, 0.01 ATM, yeah, below 1% of ATM. Air gap is just air gap. You just prepare the cold water in this case. So you could have some dews formed on the surface and take it out. So obviously VMD has the highest flux or performance, and it has less prone to the wetting and membrane fouling. So one thing that we couldn't change is that this vapor pressure. So we have 100 degrees Celsius, vapor pressure is actually 760 millimeter mercury. And then it goes down to 25 degrees Celsius is approximately 3%. Okay. So if you could lower the pressure, okay, below this vapor pressure at given temperature, then water evaporation starts. And then actually the right-hand side is actually concentration of water and vapor phase. However, this is good news that we could understand design the membrane distillation plant or processes. However, the real bad news is that nobody can change this line. Yeah, water latent heat is given. It stems from the molecular structure and binding of the hydrogen and oxygen. So therefore, no one can effectively change this, which means that we always have to pay a certain amount of latent heat to evaporate the water. So no matter what you believe or not, and this is a shocking news that 21st century, the modern sciences, we do not know the water evaporation exactly. Yeah, we just know the equilibrium phase, but we kind of do not know the dynamic phase of water evaporation rate or condense rate. There's no theory that actually matches the experimental data. There's a very basic theory that requires certain parameter or calibration, but we don't have anything very accurate and fundamental theory that explain everything about the water evaporation and condensation. So this is actually my latest work that we actually make a hollow fiber module and do heat transfer CFD simulations. And then based on this module and the locations inside the hollow fiber and outside, we have a very nice concentration and the velocity profiles. And then our result is almost yeah, well in good agreement with the experimental result. So hollow fiber is like kind of something like your straw, although the usage of straw is forbidden right now. You put a lot of hollow fibers and put the cold water inside or hot water, and you're the shell side outside, and you actually have a different temperature. So let the two different temperature flow cross the flow in opposite directions and do the heat exchanger. And then while the heat is exchanged, then water evaporates on the surface and migrates to the other case. So the problem that I had so far is that, well, we have hollow fiber, which is quite important because the packing density is very high. So given volume that you could store a lot of membrane surfaces, but industrial application, we usually have at least 1,000 or up to 5,000 hollow fibers in one module. But most of theories that available is it takes care of only one hollow fiber, and there's no way you could do this larger scale simulation using CFD. That is mainly due to we don't have any meshing algorithms. So this is what I just did recently, and how it connected. So technically, I recently calculated how much desalination that we need. One is, well, we have a population 350K know-how, a residential population, and then the statewide water consumption is this much. So we can just multiply, yeah, perform, let's say we kind of provide or supply 10% of statewide water consumption using reverse osmosis. That is 90K tons per day. And applied pressure for reverse osmosis usually about 1,000 psi. And the power you need is about 7,000, yeah, 7,000 kilowatt. And electricity rate for residential is 30 cents, but industrial rate is a little bit low, but just use a 30 cents per kilowatt hour. So technically, you have a couple of calculations in here. So if we want to produce 10% of the water that we need using reverse osmosis, then technically we have to pay like 17 cents per day. Yeah, which is not a bad deal. Okay. And then, but other sense, there's certain dilemma. The more we produce fresh water, then actually we actually get the concentrate, which is the leftover salt. So for 10% reverse osmosis production, which is a 90,000 tons per day, and the weight-to-weight percentage of salt per water is 3.5%, which means about 3,000 tons of salt, which is salt, yeah, really a salt, approximately 2 meter by 40 meter by 40 meter size of salt is produced every day. So reverse osmosis is a very mature technology, and membrane distillation is also not that hard to implement. However, once we desalinate the water, then the leftover salt is really hard to handle. Yeah, because especially in Hawaii, that no ocean discharge is allowed. Okay, fundamental principle is there's no single device can do everything, and all the processes should be well linked in an organic way. And overarching goal is a no zero chemical discharge. That is actually, it became the crazy idea, impossible, but right now it became almost like a standard of all the desalination applications. Net zero power consumption. So using the leftover resources, electricity or temperature gradient, concentration gradient, you could make power little by little. Therefore, to operate, you should start with certain power, but at the end, in the steady state, the power consumption is almost zero. Therefore, it is most likely self-supporting or self-sustaining process. That is actually the future way of desalination, especially in isolated places like Hawaii. And if possible, then there could be a way that you could produce certain revenue. Yeah. So one way is that you could sell out the salt in a way if you could, but there are certain laws out there to prevent it. But however, there's a certain things that we could work on to make certain net revenue by this desalination. So concluding remarks is that Hawaii has a lot of groundwater. It was more than what we need. However, especially in this year, we had a drought and then sea level rise and climate change. We never know whether we're gonna have enough rain to be stored in the ground. So this is time to somehow start preparing the future. Renewable energy desalination is highly depends on locality, meaning that we need to have a local inexpensive energy sources. It depends on the where you apply this technology and local technology and local supplies. And then the public perception is also important. We don't want to have the TMT or rail type of protest by public. So the initial education and outreach to the real users, those are public, is quite important than what we think. A recommended one is forward osmosis can be used for liquid phase concentration, but not desalination. And pressure retarded osmosis could be used as a supplementary to generate the power. The membrane distillation is also important because it has pros and cons. Rejection of salt is better than reverse osmosis, but the power consumption is not way lower than the reverse osmosis if we have to boil all the water. So again, the locally inexpensive heat source is a critical factor to have this renewable desalination. And then other sense is that when we design this project, and all the designs are very unique and soar, therefore it is not likely selling iPhone. So iPhone, I mean, devices are all same, then everybody enjoy the same service. But the desalination plant is very localized and unique. Therefore, it should be a kind of a convergent kind of project combining socio-economic cultural agreement. Without this agreement and starting desalination plant is, I mean, design or project is very dangerous. You don't know when it's gonna be stopped. Okay, so that's it for today. And I tried to give a better view or overview of desalination. And 21st century desalination is not just like removing salt, but it is a very highly correlated to the other neighboring industry as well as a regular human life, also the public perception. Yep, that's it for today. Thank you.
Okay, thank you so much for the great talk. And so we have two questions from the audience. First one is you just to briefly mention, answered, but this is Israeli plant, Sorek plant, the seawater RO plant.
Hmm.
Yes, the answer is yes. Okay,
Yeah,
and what is the cost of power that the, that plant uses?
I'll say again.
The Israel power plant, the plant, the seawater RO plant. So what is the cost of the power, or just what is the power requirement
Oh, okay.
consumption?
Okay. So I should say in this way. um, the Sorek and the Ashkelon plant, and their price is like 50 cents per ton. This is amazingly cheap. Um, but not everywhere that cost could be made. The reason is usually big desalination plant is co-hosted with the big power plant. So you have a power plant and you have a desalination plant. They just exchange resources in free. So power plant, some of the seawater intake that is kind of warm, but if we if that seawater is used as a cooling, partially the cooling of the power plant, the temperature increase up to 40 degrees Celsius, and then the viscosity decrease down to half. So you actually need the half of the pressure to pump out the seawater compared to the 20 degrees Celsius of the seawater out there. And then desalination plant try to produce fresh water to have a clean infrastructure to the power system, power plant. And the power plant give the very cheap cost of electricity. So technically, applying this residential or industrial power rate to the current the small desalination plant is almost nonsense. Yeah, they should have certain agreement with the government and the nearby the infrastructure. Yeah.
So follow-up question. So how the Israel deal with this kind of remnant or byproduct of salt? So when they just finish um, the desalination,
I
so they
didn't.
should have,
Please say again.
yeah, this is my question. So
Yeah.
basically how they deal with the discharge or the byproduct salt product after the desalination. So they actually have a lot of the, is it like a discharge to the sea or?
Okay, so I think the Okinawa is the best example. And Okinawa plant and their intake and discharging pipe system is only 100 meters from the shoreline. And then pipe size about, I believe it's 1 or 2 meter. So, and then the two ends of this pipe is only separate from a few hundred meters. So meaning that if we have fast ocean flow, then discharge is just discharge. You just throw away to the back to the ocean. But Hawaii, it's not possible. So, but this discharging is not preferred in anywhere, especially in the Mediterranean Sea. Then they don't like to discharge anything back to the ocean, which is Mediterranean Sea is kind of confined. So the new paradigm is a zero discharge. So technically, zero discharge means that you get 100% of salt out of water. So the paradigm changes. The previous paradigm was how much we could get more water out of seawater. But the current paradigm of desalination is how could we possibly get 100% of salt out of seawater? And the leftover is fresh water that you can do whatever you want. And that is actually very, very challenging. One way is making salt. Yeah, you could just have a salt pond and let the water evaporate. That is a very, very traditional technology. But in Hawaii, the Kauai has a little bit of a salt pond, but the salt couldn't be couldn't be sold, and that is out of the against the law. And then other thing that we tried is membrane crystallization. So membrane desalination is actually take out the water based on evaporation. But if we control the membrane distillation a little better, then we could selectively crystallize specific salt because all the salt has a slightly different pKa values or solubility product values. Depending on flow and temperature, then we could selectively generate the crystal of like sodium and potassium in a different stage, but that is actually under the active research right now.
Okay, thank you. And another question from David Beck. So do you have any information about sodium ion battery potential for desalination?
Ah, okay. So let me tell you this way. Number one, and to make it short, I don't know. Second of all, um, membrane actually have 2 to 3 different types of research. One is material development. yeah, material scientists and polymer scientists, they make thousands and millions of different types of materials and publish paper. And then environmental engineers, we usually focus on lab scale experiment. Yeah, we make our system as small as possible to represent at least like a pilot scale performance. And then there's actually the company people who actually make the plant and operate and get the data and analyze it. But the bottom line is that among the millions of the paper out of this material scientists, we only use one or two in industry. And therefore, it is not that safe to answer this question. However, if you find a good phenomena or performance in a lab scale experiment, and it will be similar to the vaccine development, it will take a certain amount of years to make it commercialized. So potential, I don't know. The answer is I don't know. But the paradigm should be changed that the material development should be top-down way, not the bottom-up.
Okay. David said thank you. And so from Megan, do you know on average how much building or desalination facility costs?
Okay. Right. So this is actually kind of similar to the OTEC plant, the building, new OTEC plant. But the thing is that you actually have to have some good finance if you really want to start a new plant. And then certain agreement from the government and then contract, then you actually amortize the thing. So it's out of my discipline. So I kind of do not know. But the cost-wise and things are included in the actual cost. So here, how much? No, initial cost, I don't have anything. But the one thing I can tell you is that the cost, no matter what, is a sales cost or this initial investment, it fully depends on the size. So if you have a bigger size of plant, then cost decreases exponentially. I mean, power-wise.
Okay, thank you.
Okay, so I guess the last question is from audience is, does the Laplace pressure induced by the hydrophobic membrane influence the water evaporation rate?
That's the must. So I didn't include the hydrophobicity, but we actually have to make the membrane for membrane distillation hydrophobic as much as possible. Yeah.
Mm-hmm.
If it's hydrophilic, then the water just gonna pass through the membrane pores.
Okay, so audience, if you don't have any questions, okay. Yeah, thank you so much for the great talk. And so, and if you have any further questions, so please contact Dr. Albert Kim, and his presentation, I believe, will be available on his website.
Sure,
and also
sure.
video will be available in a week or so in our website. Thank you so much.
Okay, thanks.
Thank you very much, Albert.
Thank you.